Welcome everyone to 11.9 representations of functions as power series. Now in 11.8, when we first introduced power series, we had one example where it said, express this power series in a closed form. And that's essentially the idea that we want to take and go running with, but then in the opposite direction. If we have a closed form of a function, can we go ahead and represent it as a power series? So kind of the problem reversed. So in this section, yes, we're going to understand how functions can be represented as power series, and then finally, we're going to learn how to differentiate and integrate power series. Let's get to it. All right, so our big theorem comes from this idea of geometric series, and that is 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus dot dot dot, which is the same thing as the sum from n equals 0 to infinity of x to the n. And from our good old geometric series days, we know that the absolute value of x, or r, should be less than 1. So that's our radius of convergence here if our a is 0. Okay, so again, this is an idea that has to do with geometric series, except for instead of r, we have x. So let's learn to express some different functions as power series. So here I have 1 over 1 minus 3x squared. So I'd like to think of u as 3x squared, because then I would have 1 over 1 minus u. So this would be the sum from n equals 0 to infinity of u to the n. Well, let's go ahead and substitute back in, right? This would be n equals 0 to infinity of now 3x squared to the n. So you can see this is how we can represent 1 over 1 minus 3x squared as a power series. If we'd like to, we can go ahead and use property of exponents to kind of get the coefficients isolated and the variables isolated. So this is going to be 3n times x to the 2n. Okay? Then it asks, find the radius of convergence. Well, we know that u in this case, the absolute value of u must be less than 1. So therefore, the absolute value of 3x squared must be less than 1. So therefore, the absolute value of x squared must be less than 1/3, right? Dividing by 3 on both sides. And then essentially taking the square root of both sides to some extent, we can see the absolute value of x must be less than 1 over root 3. So therefore, the radius of convergence in our case is 1 over root 3. And you can see all throughout this section, we're going to be dealing with power series centered at 0, right? So our a is always going to be 0. That's how we're going to use this theorem for the most part. Okay, let's try another example. So here, this is a little bit more complicated, but still we're going to relate it back to 1 over 1 minus x. So in this case, I'm going to do 1 over 1 minus u, and I'm going to try to choose something that kind of looks like this, x over 3 plus x. So first of all, let me imagine multiplying by an x and throwing a 3 down here. So this is factoring out a 3, really. So if I factored out a 3 from 3, I get 1. And if I factored out a 3 from x, I would have x over 3. Now I need a minus, but I have a plus. So I'm going to make this minus a negative. Okay? Okay, so this is quite a lot of work to say u should be x over 3. Because then I have this 1 over 1 minus u, right? So I have this x over 3 out to the side still, and then this 1 over 1 minus u, well, we know that's the same thing as the sum of our u to the n's. So this is x over 3 times the sum of, from n equals 0 to infinity, of, instead of u, let me write negative x over 3 to the nth power. Now again, we can go ahead and use properties of exponentials to go ahead and distribute things a little bit. So let me first of all put my x over 3 inside of the summation now. This is one of the properties of summations. I can do this. And then my negative x is the same thing as negative 1 and x. So each one of these needs to be raised to the nth power. And then I also have my 3 to the nth power. So this is going to be the sum from n equals 0 to infinity of, and it looks like I have n of these negative 1s, so negative 1 to the n. And then there's the 3's, I have n plus 1 of them. And then my x's, I also have n plus 1, right? Because it's that extra x and that extra 3 in the denominator. So this is my final answer. This is how I can represent x over 3 plus x as a power series. Now my last part is, again, I want to find the interval of convergence. So remember that the absolute value of u needs to be less than 1. In this case, u was negative x over 3. So if I go ahead and represent this as 1 must be greater than x over 3, which must be greater than negative 1, using that nice theorem that we have, we can go ahead and multiply by 3 on all sides, and we get that x must be between negative 3 and 3. So if we write that in interval notation, that's just parentheses, negative 3, comma 3, parentheses. Now I'm forgetting something, right? It asks for the interval convergence, so I need to test endpoints, and I'm going to actually leave that for you to do. But if I was to just leave my work as this, you could potentially get some points taken off. Now, it turns out that this is the answer, so that neither of the endpoints is actually included, but it's important that you always check them, so that way you receive full points on all your homework, quizzes, exams. But again, I'm leaving that for you. All right, now I'm going to be moving into taking derivatives and integrals of power series. So again, we have our nice power series, we have a radius of convergence, and we're going to consider f a function defined by a power series. So that is, it has a c0 plus c1 x minus a plus c2 x minus a squared, so on and so forth. We could, of course, write this in sigma notation as the sum from n equals 0 to infinity of c sub n times x minus a to the n. So that's kind of our assumption, that f can be represented as a power series. Then it's differentiable and therefore continuous on the interval from a minus r to a plus r, and we can take the derivative. And the derivative is exactly what you would expect. So if I take the derivative of c0, I get nothing. If I take the derivative of c1 times x minus a, well, that's just c1. And you can kind of see how this goes. It's just basically taking the derivative of polynomials. So if I do this in the general case, this is actually going to be the sum from n equals 1 to infinity of n times c sub n times x minus a raised to the n minus 1. So it's essentially the power rule, except for our c sub 0 is gone, right? So that's why we start at n equals 1. Now if I integrate, well, there's going to be a constant of integration. That's my c in this case. And then when I integrate c sub 0, well, I'm going to have this x minus a. And then I could have plus c1 over 2 x minus a quantity squared, and so on and so forth. And so that's going to be the same thing as essentially integrating polynomials. So when I integrate polynomials, I have this n plus 1 on the bottom, and then I raise it to the n plus first power. C sub n's constant, that's still there, and we have my x minus a. My base stays the same. So this is going to be the sum from n equals 0 of c sub n over n plus 1 times x minus a to the n plus 1. And the radius of convergence stays the same. So that's very interesting. Okay, so let's go ahead and try this. And the claim is we can now figure out how to represent more things as power series. So if I take the derivative of 1 over 1 minus x, well, according to the power rule, negative 1 would come down and then be raised to the negative 2 power. And then the chain rule means I'd have to multiply by another negative 1. So this is the same thing as 1 over 1 minus x quantity squared. Okay, so if I take the derivative of this thing that I know what the power series is, I get my new function. How nice. So because 1 over 1 minus x is the sum from n equals 0 to infinity of x to the n, I can take the derivative of both sides, and this is going to be the sum from n equals 1 to infinity of n x to the n minus 1. So the derivative kind of acts exactly how you would expect, but this is what the result is from theorem 11.9.4. And again, the radius of convergence is r, right? Whatever the radius of convergence is originally, it originally was 1 in our case, the radius of convergence stays the same when you take the derivative. Okay, let's try another one of these. I did a derivative one. Why don't we go ahead and try an integral one? So the natural log of 1 plus x. If I take the derivative of this thing, let's see what I get. I get 1 over 1 plus x. Now I know how to represent 1 over 1 minus x, right? Or 1 over 1 minus u, for instance. So let's go ahead and write this equal to 1 over 1 minus u, and we're going to go ahead and note that u has to be equal to negative x. I guess I should actually write this down really quick. 1 over 1 minus u. All right, there we are. So then the sum from n equals 0 to infinity of u to the n, aka the sum from n equals 0 of negative x to the n, is equal to 1 over 1 plus x. Now, if I integrate both sides, I should get the natural log of 1 plus x, right? So all I need to do is integrate both sides. Well, on the left-hand side, again, integration happens exactly like it does for polynomials, essentially. So n plus 1 in the denominator times negative x to the n plus 1. There it is. And why do I have that negative, you might wonder? Well, that's because of the chain rule, right? So the chain rule, because I'm integrating negative x, there's going to be this extra negative term. Okay, and what is the radius of convergence? Well, let's go ahead and check really quick. We know that the absolute value of u must be less than 1. So therefore, the absolute value of negative x must be less than 1. And therefore, the absolute value of x must be less than 1. So I know you guys were all worried about these absolute values over here, but it turns out it's the same thing as the parentheses of the natural log of 1 plus x, because the absolute value of x is less than 1, right? So the worst case it can be is really close to negative 1, but it can't quite get there. So therefore, the natural log will be greater than 0. So we're safe. Okay, and finally, that gives us, right, r has to be equal to 1. That's our radius of convergence, according to this inequality over here. All right, let me go ahead, and I got one more example for us, a little bit more difficult. We have a tangent inverse of 1 plus x. So I want to find the power series representation of this and the radius of convergence. So, okay, well, if I take the derivative of this thing, the claim is that it looks kind of like my 1 over 1 minus x. So if I take the derivative, it's going to be 1 over 1 plus x quantity squared plus 1. So, again, I want to try to represent this as 1 over 1 minus x. So given that, it makes sense that u should be negative 1 plus x quantity squared. Then I get my 1 over 1 minus u. Okay, so that means that 1 over 1 minus u is the sum from n equals 0 to infinity of u to the n. Well, that's the same thing as negative 1 plus x quantity squared to the nth power. Okay, so again, maybe instead of u, I could write my negative 1 plus x quantity squared, or 1 plus x plus 1 quantity squared. All right, let's go ahead and distribute this n essentially a little bit. So this is going to be the sum from n equals 0 to infinity of negative 1 to the n, a nice constant, times 1 plus x to the 2n. And now my goal is to integrate both sides, right? Because when I integrate, this should undo my derivative, and I should get tangent inverse of 1 plus x. And when I integrate this right-hand side, well, this negative 1 to the n is constant with respect to x, so it's along for the ride. And then I get 1 over 2n plus 1 times 1 plus x to the 2n plus 1. That's just using the power rule right there. And then finally it asks for, well, what is the radius of convergence? So remember that the absolute value of u must be less than 1. So the absolute value of negative 1 plus x quantity squared must be less than 1. So, well, the absolute value of negative 1 is just positive 1. And then if I go ahead and essentially take the square root on both sides, I'm going to get the absolute value of x plus 1 must be less than 1. So therefore, I get my radius is equal to 1. So there we go. That's my power series answer and the radius of convergence. All right, and with that, we're all set with 11.9. Now I know what you're thinking, only one video for 11.9? Don't worry, there are 3 videos for both 11.10 and 11.11, so I'll make it up to you. All right, good luck on your homework. I'll see you guys next time.